So today we're talking about systems of equations, and a system of equations is when you have multiple equations at once. Okay? When you have multiple equations at the same time, oftentimes I'm going to be asking you to find the solution to that system. So when I say a system, I just mean multiple equations, essentially. So the solution to a system is going to be the xy ordered pair or coordinate that satisfies both equations. And most of the time, there's only going to be one point. I mean, if you think about how we graph lines, there's only one way they could intersect, right? They're either going to, like, unless they're parallel, they're always going to just hit each other one time. So for these systems of linear equations, most of the time, there's just going to be one solution. Okay, we'll see a couple of corner cases where something weird could happen, like parallel lines, for instance. But for the most part, you're just going to have one answer. Okay, the solution to a system of linear equations is an ordered pair. Okay, so it's like x comma y. It's a solution to both equations in the system. So whenever you find a solution to the system, it's always a good idea to check to see whether or not it's actually correct. So I want to show you how you would do that. So these first couple of examples are just saying, okay, hey, is this the solution to the system? So is 3 comma 1 a solution to both of these equations? So how do you think we might check that? How would we know whether or not this is a solution? Yeah, exactly. Yeah, plug them both in, or plug it into both equations. And if they both give you like a true statement, then you know it's the solution. So let's test that with these. So for number 1, we're going to test to see if 3 comma 1 is a solution to the system. We're just going to plug it into both equations. So this is my x, this is my y. We always have x before y. So plugging into the first equation, I'm just going to sort of write these out separately. So you can see x plus y equals 4. 2x minus y equals 3. So I'm going to plug in the x, 3, wherever I see x. And I'm going to plug in the 1 everywhere where I see the y. So I've got 3 plus 1 equals 4 for this equation. Is that true? Yeah, so we know that 3 comma 1 is a solution to that equation. That doesn't necessarily mean it's a solution to the system, because to be a solution to the system, it needs to satisfy both equations. You got to check them both. So if I plug in 3 and 1 to the next one, I get 2 times 3 minus 1 equals 3. So this would be 6 minus 1, does that equal 3? No. So it is a solution to one of the equations. In other words, like this point is going to be on this line, but it's not on this line. So we say, no, this is not a solution. It must be a solution to both equations. So let's test this one over here, 1 comma 3. All right, again, I'm going to do my x in pink, my y in green, just to, kind of help you visually here. So I'm going to start by just writing the two equations, x minus y equals -2, and 2x plus y equals 5, and check them separately. So I've got 1 minus 3. Now, does that actually equal -2? Yeah, so that checks out, right? And then if I plug it in over here, 2 times 1 plus 3, does that equal 5? Yeah, 2 times 1 is 2, 2 plus 3 is 5, that checks out. And you say, yes, that's a solution. So that's how you would check your answers, right? Once you get your answer, you should always kind of go back and make sure that it's actually right. Now, there are several ways to find the solution, right? This, I'm just sort of giving you it and say, hey, is this a solution or not? But what you're going to be doing all throughout this unit is trying to find the solution. And we're going to go over 3 different strategies for doing that. First strategy we're going to go over is graphing, where basically all you have to do is just graph both lines, which I know is sort of easier said than done. But as long as you graph both lines correctly, the solution is just going to be the coordinate where they intersect. So you're looking for that intersection, like where they cross. And that point will be your solution. That'll be the one point that works for both equations. So I'm going to kind of guide you here. The solution to a system equation can be found where the 2 graphs intersect. So for 3 and 4 here, the graphing part of it is already done for you. Okay? So we just want to find the solution. So for number 3, you've got 2 equations that are already graphed for you. So the solution to the system, like Andrew said, is where the graphs intersect. Yeah, right here. So what would be the solution to this system? 2, -2. All right. So if you're given the graphs, finding the answers, as long as you can identify points, pretty easy. You just find where they cross and you're done. What would be the solution to number 4? Yeah, -1, comma, -3, right there. Yeah. -1, -3. So now that you can kind of see sort of the strategy that we're using here, now comes the hard part, right? The actual graphing part of this. So we're just going to practice graphing a bunch of lines here. And please ask questions if you're sort of unsure of what I'm doing. Slow me down a little bit, because if you can't graph correctly, you're not going to be able to solve a system this way. Right? That's sort of going to be a fundamental skill in order to do this. So we'll just practice a bunch of these. Now, remember that the way we graph is going to be dependent on what the equation looks like. Okay? And really, these are going to typically fall into 2 categories. We've got 3 different equations for lines: slope, intercept, point slope, and standard form. But for the most part here, there's not going to be too many in point slope. Most of them are going to be in slope, intercept, or standard form. But the way you graph them is a little differently, right? If the equation's in slope, intercept form, you start with the y-intercept, and then you use the slope to find more points. If it's in standard form, you'll instead find the x-intercept, find the y-intercept, and then just sort of connect the dots there. So what we need to do before we start graphing is identify, how are we going to graph it? So for number 5, these are both in slope-intercept form. I'm going to make a little note. These are in slope-intercept form. Both of them, right? Y equals mx plus b. So what we want to do is start by locating the y-intercept and then using the slope to graph the line. So for y equals -x plus 3, what's the slope? I'm sorry, let's start with the y-intercept. What's the y-intercept? The y-intercept is 3, so we could plot that. And then what's the slope? -1. So if the slope is -1, starting with that y-intercept, we're going to go down 1 and then to the right 1. And just plot as many points as you can along that pattern. Draw your line, and that one is done, right? Now we'll graph y equals x plus 5. For this problem, the y-intercept is 5. And what's the slope? Since it doesn't look like there's a coefficient on x, what number is implied there? -1. All right, so we'll start with the y-intercept of 5. And notice, my slope is 1, so I'm supposed to go up 1 over 1, but there's not really any room to do that. So I'm just going to take that pattern backwards. Now, once you've graphed both lines correctly, what's the solution? Where do the lines intersect? -1, 4. All right, so yeah, we found our solution right here. For number 6, once again, both of these are in slope-intercept form, y equals mx plus b. So for y equals 1/2 x plus 2, we want to find the y-intercept and the slope. So what's the y-intercept? 2. And the slope is 1/2. So you see how this slope's a little bit more obvious. It's just right there. You just have to know that if there's not a number there, that it's either 1 or -1, depending if it's positive or negative. Okay, so let's go ahead and plot that. Y-intercept is 2. The slope is 1/2, so I'm going to go up 1 to the right 2. I've got a positive slope, so the line should be going up from left to right. Okay, so there's the first line. If I have y equals -1/2 x plus 4, in this case, my y-intercept is 4. And my slope is -1 over 2. So we're going to start with the y-intercept, 4. My slope is -1/2, so I need to go down 1 to the right 2. Down 1 to the right 2, we sort of found our solution right away, but I'm going to continue the line just so I have the whole thing graphed out. Notice that these two lines intersect at 2, 3, so that's my solution. In other words, like, that's your answer. That's what you're looking for when you're trying to solve this system. For number 7, once again, these are both in slope-intercept form, so we're just going to kind of stay the course here. Y equals 1/3 x is going to be the first one. Y equals -2/3 x plus 3 is the second one. Now, if I see 1/3 x, but I don't see anything being added, what's the y-intercept? 0, yeah. So the y-intercept 0, the slope is 1/3. So I'm going to start at the origin where the y-intercept is 0. My slope is 1 over 3, so I'm going to go up 1 to the right 3. And it looks like I'm going to fall off the grid over here, so let's take it backwards. For this one, the y-intercept is 3. And the slope is -2/3. So I'll start up here at 3. I go down 2 over 3, down 2 over 3. And continue it backwards. So you can see where the solution is going to be. So what's the solution to this system? 3, 1. Yeah. For this last one, are these equations in slope-intercept form? No. So you can put it in slope-intercept form if you're okay with that, but I'm going to show you to sort of revisit how you graph equations that are in standard form. So both of these are in standard form. right? The ax plus by equals c form. So when your equations are in standard form, the strategy for graphing is a little bit different. Instead of plotting the y-intercept and then using slope, you sort of bypass the slope altogether, and instead you try to identify what the x-intercept is and the y-intercept is. And so back when we went over how to graph these, I called this the cover-up method, where you cover up the term you're not interested in and then solve the remaining equation for the appropriate intercept. So let's start with 2x plus y equals 5. Okay, so to find the x-intercept, what I need to do is cover up y, essentially substitute 0 in for y, and then my equation is 2x equals 5. So if 2x equals 5, what does x equal? 2.5, right? So that's my x-intercept. 2.5 is going to be right about here. And then my y-intercept, I'm going to cover up the x, right? Substitute 0 into x, and I get y equals 5, which is already solved, right? So if that coefficient's 1, you don't really have to do anything. So my y-intercept is 5. So it looks like the slope here is like down to, this is -2 here. So I'm going to fill in the gaps. There's that line. Now let's look at the second one. So we have 3x minus 2y equals 4. So the x-intercept, I will graph by covering up the y. So this one's going to be a little tricky. 3x equals 4. So let's solve for x here. If 3x equals 4, this one's going to be a little ugly, but what is this going to be? What's 4 divided by 3? Yeah, 1.3 repeating. Okay, so that's my x-intercept. 1.3 repeating is going to be right about here. And let's find the y-intercept. So the y-intercept is going to be, let's see, -2y equals 4. So if we cover up the x. So if -2y equals 4, what does y equal? What's 4 divided by -2? -2. So the y-intercept is -2. Now, I think we can sort of pinpoint where the solution is going to be. Even though the slope here is kind of a little tricky, right? You go up 1 over 1 1/3. Up 2 over 1 1/3 would put us like, let's see, up 2 over 1 1/3. Up 2 over 1 1/3 would put us like right here. Our solution is right here. So what's the solution going to be? Yeah, 2, 1. All right, so let's look at the back. So these are, at the beginning I said there was like a couple of corner cases where, you know, two lines would not have like one specific solution. So it is possible for a system of linear equations to have, we know obviously it's possible to have one solution, but it's also possible to have no solution. And then one weird case is where we have infinitely many solutions. Okay, so here are those three cases, right? The lines can intersect. Obviously, we just saw 4 examples where the lines intersect. So this is going to be the most common thing. If the lines are parallel, like if the slopes are the same, one of the pieces to lines being parallel is that they never intersect. So if two lines don't intersect because they're parallel, then you could say there's no solution. There's no point that is going to satisfy both equations. Now, this says the lines are coincident, but I'm looking at this and I just see one line drawn. So what am I trying to say here? In what case would there be infinitely many solutions? What do you think, Owen? Yeah, the lines are basically the same. Like if the two equations in your system are identical, then they're just going to be like right on top of each other, and therefore the solution will just be all of the points that are on both lines. So there'd be infinitely many of those. So what I'm saying is that like if you go and graph both lines, and they're just on top of each other, they're the same line basically, then you would say there's infinitely many solutions. So let's do a few more. Now these are going to have sort of weird things happen sort of purposefully. Let's start over here. Notice both of these equations are in slope-intercept form. So we'll start by graphing the y-intercept and then use the slope. So for the first equation, the y-intercept is 2, and the slope is 3. So I'm going to go up 3 over 1. Now, even before we graph this next line, what's our answer going to be? Let's see if you can just tell by looking at the equations. There's going to be no solution because they're parallel. And how did you know they're going to be parallel without graphing them? The slopes are the same, right? If you look at these slopes right here, they're the same. So unless they're the same exact line, which they're not because they have different y-intercepts, they're going to be no solution. So let's just go ahead and finish graphing it out. So the next one has a y-intercept of 4. The slope is 3. Your line is going to look like this. Clearly, they are parallel, so you're going to say there's no solution. That will happen every time the slopes are the same and the y-intercepts are different. If the slopes are the same and the y-intercepts are the same, that's where you have infinitely many solutions, because they're the same line. All right, let's try number 12. In this case, the first one's in slope-intercept form, so let's go ahead and graph that. Y equals 2x plus 3, so you're going to start at 3. The slope is 2, so up 2 over 1. Continue that pattern backwards. And the second one is really not in any form. It's not in slope-intercept. It's not in standard form. So we need to modify this to get it into a form that's graphable. I think the easiest, you could do a couple different things. Like if you subtracted the 4x, you could get it into standard form. How would we get this into slope-intercept form, though? Like y equals mx plus b form. What would we need to do with this 2? Sort of get rid of it. Yeah, divide everything by 2, right? So we're going to divide everything by 2. And that gives me y equals 4 divided by 2 is 2, 2x plus 3. Now right away, what's the deal here? Yeah, it'll be the same, right? So these are the same lines. So we say there are infinitely many solutions. For number 13, both equations are in standard form, so we're going to approach the graphing by doing the intercepts. So the first one has an x-intercept of 6. Now that's going to be way out here. It's not very convenient. And then what's the y-intercept going to be for that first one? Can you just see it by looking at the equation? Like if I cover up the x, I get 3y equals 6. So y equals 2. Okay. So if I'm going down 2 over 6, that's equivalent to going down 1 over 3. For the second one, if I cover up the y term, I get negative x equals 3. So the x-intercept would be negative 3. If I cover up the x term, I get negative 3y equals y. So the y-intercept would be negative 1. This slope is down 1 over 3 as well. So it wasn't super obvious by looking at the equations, but what types of, what's going on here? Yeah, they're parallel. So we say there's no solution. We got one last problem, then I'll have you start working on some of the homework problems with the rest of the time. It says a test has 20 questions worth a total of 100 points. The test consists of X true-false items that are worth 4 points and Y multiple choice items worth 8 points. How many of each type of question are on the test? So we need to set up two equations having to do with how many questions there are and how much are they worth, and then graph them and find the solution. So it says there are 20 questions. So if we take the number of true-false questions X and add the number of multiple choice questions Y, there will be a total of 20. Right? Where X is the number of true-false, Y is the number of multiple choice. So that the first equation is just going to be about like how many there are. The second equation is going to be referring to how much are they worth. So the true-false questions are worth 4 points each. So 4x plus the multiple choice questions are worth 8 points each. So plus 8y equals a total of 100 points. So this is the system that we're going to use to graph. We want to keep, I don't want to scale this until I actually figure out some more information about this. Both of these equations are in standard form, so we'll approach it from the perspective of intercepts in terms of to graph this. So let's figure out what the intercepts are. So like for this first equation, what's the x-intercept? 20. And what's the y-intercept? 20. So I know on my graph I got to at least go out to 20, right? So let's think about the next one. What's the x-intercept here? See, this one won't be as obvious. We got to cover up the y. And so for the x-intercept, we have 4x equals 100. So what's the x-intercept? 25. And then for the y-intercept, we have 8y equals 100. Oof. Does 100 divided by 8, does that work out? Maybe it does. It's 100 divided by 8. Yeah, 12.5. That's half of 25. So let's try to graph this. All right, we'll start with the first one. So we got to go at least out to 20. Actually, we got to go out to 25. So what would be like a good scale to use here, do you think? Maybe 5s? So let's see, 5, 10, 15, 20, 25. I don't really need to go out past that. 5, 10, 15, 20, 25. All right, so let's graph the first one. Both the intercepts are 20. And then for the next one, this is going to be a little tricky, but the x-intercept's 25. The y-intercept is 12.5, right in the middle between 10 and 15. So if I graph this, I might even use like a straight edge to do this, because I'm not really sure what the slope is here. Where does it look like my solution is? (15, 5). So how many of each type of question are there? How many true-false questions are there? Keep in mind, this coordinate is 15, 5. So how many true-false questions are there? 15, right? So there's 15 true-false questions And how many multiple choice? 5. And 5 multiple choice.